Thank you, Victor, for the introduction, and thank you all for being here until the last talk of the afternoon. I hope I will catch and preserve your attention with this topic of the optimization of trigonometric polynomials. This is joint work with my PhD advisor, Evelyn Hubert from Sophia Antipolis, and also with Philippe Moustrou from Toulouse, although Philippe was still in Tromsø when we started this project, and also with Claudia and Rina, who is professor in Tromsø. And in this talk, I will mainly focus on the part on optimization. I will not go into too much detail of crystallographic symmetries. For this, I will provide some examples. And then by application, I mean an application in algebraic combinatorics, which we will come to in the end. So optimization in Poema means that we replace constraints of optimization problems by positivity certificates, such as sum of squares, quadratic modules, reorderings, whatever. And so I will start with a little historical overview and draw the connection to invariance. So we already heard and know that Hilbert proved in 1888 that the polynomials, which are homogeneous of degree 2D in n variables, can be written always as sum of squares, if and only if one of those three cases holds. So if the degree is 2, if the number of variables is at most 2, or if you have this special case. And since 1900, it is known as Hilbert's 17th problem, if you can write still any homogeneous polynomial as a sum of squares with rational, so as a sum of rational squares. And this was proven to be true by Artin 27 years later. But what is not so well known is a question that was posed in an article by Harper and Botha in 1970. And the question that is formulated here a bit hand-waving is, what about invariance? What about linear invariance? The question is, can we write an invariant polynomial always as a sum of invariant squares? And this is not true. Here is a very easy counterexample. The group that we are looking at is the group of sign change, plus minus 1, which acts on the real numbers by change of sign. And the polynomials which are invariant under this action are all polynomials which can be written in x squared, so for the even polynomials, essentially. And clearly, the polynomial x squared itself is non-negative on the real numbers. However, you cannot write it as a sum of invariant squares, because if you assume this for a second, so here if you write the sum of squares in something invariant, so they have to be polynomials in this x square, and you square them again, and you will see that x has to be a sum of squares. Now that's not possible. And this was an example that was used in an article by Tobias in 1978, who generalized this statement, and when it works, to the case of the symmetric group that acts on Rn by permutation. And he showed that there exists some mysterious polynomials hi, which are positive and invariant, so that every polynomial, such as this f here, for example, which is invariant and positive, can be written or has such a representation here, where the Si are sums of squares of invariants which are rational. This theorem was generalized in 1985 by Puccisi and Schwarz, who showed that this is in fact true for any compact Lie group as well. So these results appeared before we had Positivstellensätze such as Rütgen or Putiner. And with these Positivstellensätze, we could already answer this question. But the main problem here is how to find those hi, right? So assuming that your ring of invariants, so the ring of polynomials which are invariant under your group action, can again be written as a polynomial ring in some theta 1 up to theta n. Then what you need to do is you need to describe the orbit space right here, which is the image of Rn under the invariance, and you need to write this as a semi-algebraic set, as a basic semi-algebraic set here in this case. with only inequality constraints. And the polynomials in this theorem of Puccesi and Schwarz are exactly those polynomials which you obtain when you replace the variable with the fundamental variable.
Can I ask a question?
Yeah.
Are you saying the orbit space is a basic semi-algebraic set?
Not always, no. Not true. In this result of Puccesi and Schwarz, it actually is.
But you wrote it looks like.
Yeah. So okay, I mean in this result, it is a basic semi-algebraic set.
So it's an assumption.
No, it is true for any compact Lie group with an action on a real representation space.
I thought it was described by polynomial matrix.
It's the same thing, right? If you have a polynomial matrix, then the positivity locus of this matrix can be described as a semi-algebraic set by the coefficients of the characteristic polynomial, if the matrix is symmetric. And or I mean those are the leading principal minors, right? And vice versa, if you have a description of a semi-algebraic set as this one, you just take the polynomials that describe it, put it in a matrix on the diagonal, and this matrix is then again positive semi-definite in this place.
So I think the result of Puccesi and Schwarz is that the orbit space is a semi-algebraic set.
Yes.
But I'm not sure basic.
The result.
I don't think it's basic in general. As far as I remember.
The result states, or the result of the paper is how you construct these polynomials HI. And they show that you obtain them from a matrix, which is given by differentials, which come from a Gram matrix. And essentially these polynomials. So what I want to discuss in this talk is what happens when we go to multiplicative invariance. And I want to introduce this with an example. Same group as we had before, the group that x that is plus minus 1. But now it acts on the ring of Laurent polynomials, and it doesn't act by change of sign, but by inverting the coefficients. If we show that the ring of invariance is a polynomial algebra in the variable x plus x inverse over 2. And now, similar to this example from the Puccesi article that we saw, let's look at this polynomial right here. Q minus something that's clearly inverse. This polynomial is non-negative on the complex unit circle. T here stands for compact torus. And we can write this polynomial f as polynomial g in this fundamental invariant, where g looks exactly like this. And now, to write this as a representation that we know essentially from quadratic modules, we can write this as this square right here, plus the polynomial that describes this orbit space right here as its positive. The orbit space in this case is essentially the interval minus 1, 1. It's represented by the polynomial 1 minus z squared. And the result that we obtained then with Bordia is to show that the orbit space of such a kind of action is again a basic semi-algebraic set, and it is given as a positivity locus of a meet quadratic form or its associated matrix polynomial, which is P. And this works for so-called crystallographic groups, which are the Lie groups of crystallographic root system. We don't know what that means. Maybe think of it as the symmetric group of sign change, and so on, that acts on the exponents of these Laurent polynomials here. It doesn't act on the variables of the polynomial ring itself linearly. It acts on the exponents. So why do we care about these multiplicative actions and about these root systems and bi-groups. So here's a motivation that I found quite interesting. Recently, the Fields Medal was awarded for showing that you obtain an optimal packing of the 8-dimensional space with spheres if you choose as centers the points in the root lattice associated to the E8 root system. And when you look up this E8 root system, you usually find this image right there, which I took from Wikipedia. And I found this quite interesting and motivating that you have these connections. And in the end, in fact, I will give a connection to the problem in algebraic combinatorics that is related to these root systems. Okay, so after this introduction, let me make precise first what is the goal of the talk that I have right here. As I teach in the title, it will be the optimization of trigonometric polynomials with this kind of symmetry. And then I will talk about how we solve this problem. And I propose a way that will hopefully prove to be very efficient. I will make explicit the semi-definite program that arises from this. So here we use a Dacier type relaxation again. And then we will go on to an application to bilevel problems, so-called max-min problems, and finally look at this application that I was talking about. So the example that we saw before with the multiplicative action was on the ring of Laurent polynomials, x and x inverse. And on this ring, you can essentially define the univariate Chebyshev polynomials. So here's the definition. TL is a univariate polynomial, not Laurent polynomial, univariate polynomial, and you define it via this property right here. As I said before, every polynomial that is invariant under inversion of this x can be written as such a polynomial. So this is, and it can be written uniquely. So this is a well-defined definition in the spirit of these multiplicative actions. And you can generalize this with these crystallographic groups to a multivariate setting. I will not go into detail how you do this. Essentially, what you need is the ring of invariance, written again in fundamental invariance. And then we define this polynomial T alpha via this property that just mirrors the univariate case. And from this, you don't only obtain one polynomial associated to alpha, you can actually obtain one for any kind of group that you have. So you obtain a whole family of polynomials. Good fundamental invariants, for example, are orbit polynomials or character polynomials. And we essentially use these to show that the orbit space of a polynomial with coefficients C alpha. And we all want to find the infimum on the semi-algebraic set, which is the positivity locus of some matrix polynomial P. Take, for example, the one from the orbit space. Yes?
Excuse me, what are the capital theta alpha?
So those are invariant elements, which are chosen smartly, let's say. Explicitly, those are the orbits. So it's the sum over all monomials in the orbit of x alpha divided by the group order, if you want. This is, for example, a choice that you can make for these fundamental invariants. And yes, so at this point, we could already say, okay, yeah, easy, we can do this. Those T alpha, those are just some polynomials. We write them in the standard monomial basis. We express the matrix P in the standard monomials, and we use maybe the coefficients of the characteristic polynomial of P to obtain a classical semi-algebraic set, and then we go to the quadratic module, and we do everything with brute force maybe. But what we propose is two things. First of all, you have to exploit that you have these Chebyshev polynomials, and second of all, to exploit that you have this matrix right here. And this is not something new. So people have looked at symmetry adapted basis to do these kinds of things. And the novelty here lies in a good definition of the degree of a polynomial, which is closely. And what this means in the end is that we reduce the size of the matrices that appear in the semi-definite program. Yes. Equivalently, I mean, this is why this talk is called optimization of trigonometric polynomials. This optimal value f star is also the optimal value of such sums, a linear combination of exponentials, under the assumption that the C alpha are invariant under the group. What does that mean? The group is a bi-group. It's a finite group which has a representation over the integers. And what I mean by V invariant is that the coefficients for all elements in the orbit under this group of alpha are all equal. So this is a special, or this is more general than symmetric, where you say that C alpha is C minus alpha. You now have a whole group acting. But what I assume at the same time is that these coefficients are real. On the other hand, we can go to multivariate Laurent polynomials and optimize them on the compact torus. And this is, for example, an important application for this was already something we saw yesterday in the talk of Hugh, who was citing this book by Dumitrescu on the on positivity of trigonometric polynomials in signal processing. In this book, what is mainly considered are univariate polynomials, and what happens when you take products of those to generate multivariate polynomials. These polynomials that I was talking about that are defined by some crystallographic symmetry don't appear in this book. But on the other hand, what is considered are polynomials with complex coefficients. And we also saw, at the ISA conference this year, this here on the compact torus, for example. And another instance where people consider optimization of specific polynomials are the circuit polynomials, or due to that, the sums of arithmetic geometric what does the E stand for? Anyway, exponent. Exponent, yeah, thank you. So, yes, so these topics are related to each other, but what we want to do is we don't want to use the Chebyshev theorem or spectral factorization. We want to use classical polynomial optimization to find this optimal value and maybe adapt the techniques of the Lasser relaxation a bit.
Sorry,
yes.
Does that formula have anything to do with the Poisson summation formula? Or?
I don't know. I assume you're referring to. Okay, maybe later. So here's an example of what we might want to optimize, and to show how writing it as a Chebyshev polynomial would simplify it. We take, for example, the lattice of hexagonal points, which is not all of these. I mean, the lattice that is spanned by all of these points that you see here, essentially omega 1, omega 2. This lattice is isomorphic to Zn. And we look at the orbits of specifically these 3 points right here under the symmetric group. Don't need to calculate it. It's the blue, the green, and the red points here on the boundary. It doesn't have to do anything with the interior here. And the goal is to infinize this expression here of exponentials for every point which is in this set. And as I just said, this is clearly invariant. This support of this trigonometric polynomial is clearly invariant under this group action. So we can write it as generalized Chebyshev polynomials. That goes one. And the indices here stand for the generators of the lattice. So omega 1, omega 2, this is 2 omega 1, this one, omega 1 plus omega 2, this one. And so on. What you see on the right hand side is the space on which we have to optimize. This is this orbit space that I was talking about. And this is what we described in the result with Hubert and Riener by a hemi-quadratic form. So we know the polynomial description for this set. Okay, so now I said that we want to adapt the Lasserre moment relaxation a bit. This is the goal, and what you can do clearly is first of all write it in two different ways. One is measures, one is with positivity, as we know, and already have seen several times. And the idea of Lasserre was to replace measures with moments or pseudo moments when we go to finite dimensional spaces, and to replace this positivity here with positivity certificates, such as sum squared. And a later result by Didier Henrion and Lasserre was using a similar approach, where they use actually that you have such a matrix constraint right here. And this is what we will use as well. So yes, you have the positivity, you have the measures. We're going over the measures here, and I will try to make it short. So for a linear form, you can define the Henkel operator, which takes a polynomial and maps it to the dual, this function right here. And if you now choose as a basis for the polynomial ring these Chebyshev polynomials that I was talking about, and you choose as a basis for the functionals, the dual basis, your matrix looks like this, indexed by elements in n to the n. So that's a problematic definition, because when you just use the standard monomial basis, you know that when you multiply two monomials, you get another basis element. This is not true here. This is, you need the recurrence formula for the Chebyshev polynomials. This is the univariate case. This is the multivariate case. And so we need to do this, we need to apply this recurrence in order to know what the basis, what the matrix elements are. Now, the next step of the realization is to truncate, right? We have this recurrence right here. Let's look at an example. This is our group, not so important. Let's say the y alpha are the moments. And now we write down this matrix. So the problem that arises is if you look at the 3×3 entry, we multiply the Chebyshev polynomial associated to 0, 1, 0 with itself. And now we suddenly obtain something that is that has as an integer vector absolute 1 norm 3. So how is this possible? This should not happen. And now if we were to truncate, so, we cut this matrix off here and here with the notion of classical degree, so we cut it off at degree 1. We expect it to only contain monomials of degree 2. It's not working. So this classical degree is a problem. And what you can introduce when you have such a Y group is a weighted degree, which is given by such a scalar product right here. This O0 is a vector that is associated to this group and to the root system. And it's, I don't have time to go into it, but if it's the classical degree, then this is just the vector of 1, 1, 1, 1. And here you have to choose this vector if you want to show the following property. So we want to ensure that our moment matrix only contains the proper degree monomials. And we define this vector space right here, which is spanned by all Chebyshev polynomials up to degree at most d, up to weighted degree at most d, sorry. And then you can show that this that these spaces form a filtration. So that means their union is a polynomial, and if you multiply two of them, you end up in what is given by the sum, essentially. The first property is very easy to show. The second one involves properties of the Y group. And now we can truncate, right? We can define this truncated angle operator right here, which takes a polynomial of degree of weighted degree at most d and maps it to a functional. And this works if the functional is defined on the space of polynomials of weighted degree at most d. So this result here is essentially basis independent until this point right here. So if you have a functional that has a representing measure, and by that I mean it has a finite Borel measure, then you can show that the matrix of the angle operator is positive semi-definite. And now this matrix right here of the truncated angle operator is well defined, and basis independent, you can show that it's also positive semi-definite. What do we do with the constraint? Remember, this is the space on which this is the semi-algebraic set on which we optimize. And we have this matrix P, whose entries can be written in the basis of Chebyshev polynomials. Now I write like this, these P gamma right there, they don't denote the coefficients of the basis elements. And now we define the localized angle operator, localized at this matrix, by choosing B to be the highest weighted degree appearing in this matrix divided by 2. And now for such a linear form, you can define this operator again. The difference lies in the fact that you don't map the polynomial to a functional, but you map it to a matrix of functionals, essentially. So the matrix of this operator will have size, I don't know, whatever the dimension of this space here is. And the entries of the matrix, again, will be n by n matrices, or however large this matrix P here. It's like taking a tensor product with the moment matrix.
So the Z, the entries of Z are moments of a measure.
Z?
If P of Z is positive semi-definite, then Z comes from a measure.
No, sorry. Z is just, I mean, this is just the set on which we often
Take the Chebyshev moments. Where are moments here?
Where did I write moments?
The first row.
I think the moments are on the bottom right. Right?
Okay. Okay. I see.
Yeah.
Sorry.
So they are in this.
Yeah, but here this is a moment matrix.
But that's isn't it the P matrix that you shown? It's a different one.
No, this has nothing to do with the constraints.
Okay. So
This is the moment matrix when you write it in the basis of Chebyshev.
And then what you show is the localizing matrix associated to the P, which is a matrix with polynomial entries, right? P of Z.
P of Z is a polynomial matrix, yes.
Yeah, okay.
But of course,
It's very big.
it's huge.
Localizing matrix.
It's huge. We will see how large these matrices become.
It's about doing what you said about tensor. So
Mhm.
so polynomial base alpha tensor. Choosing correct.
Yes. Yes, you take the vector of Chebyshev polynomials of basis elements in general. You take the rank 1 matrix, and then you take the Yeah. Yeah. Exactly. Okay. So then you can show, analogously to the paper of Inria and Tobias in 2006, that when the functional as a representing measure, now on the semi-algebraic set, then the two matrices of the Henkel operator and of the localized Henkel operator associated, truncated at suitable degrees, are positive semi-definite. And so we can make this relaxation right here. So, functional with a measure is placed with a functional that has intersection with a spectral.
So representing measure on the quotient, is it the same as an invariant measure on Tn, G invariant?
So here, okay. So the notation is a bit off. This is we think of this as a semi-algebraic set. And then on this set, you don't have any group action anymore.
Yeah, but so this is a quotient. So it's taking a measure on this quotient the same as taking a G invariant measure upstairs?
No. I did not think about that.
Okay.
So maybe a good question.
Yeah, it's
I vote for yes.
Yeah, me too. I think
Now we need to show that this converges to the optimal value of the polynomial under some assumptions. And it was introduced in an article from 2005 and used in this article by Orion and Tobias, were sum of squares matrices. We say that a matrix is a sum of squares. If you have finitely many matrices, Q1 up to Qk, such that you can write the Q like this. And this is by what we can also replace the positivity constraint in the optimization problem. So here, instead of greater or equal 0, we can write this. And then Ruhl and Scherer showed in 2005 that under a certain Archimedean assumption on the set, on the description of the orbit space given by the matrix P, you have equality here. It's like a generalization, not, yeah, and it's like it's an analog of Putina's positive Stellensatz for matrices. And now this is the relaxation that we proposed with the Roman matrices. This is the relaxation that you obtain with the sum of squares matrices. Here again, we use this filtration spaces as a suitable space to relax it. And then what you can show is that the sum of squares relaxation is at most as large as the moment relaxation, and the sum of squares relaxation converges to the optimal value under this Archimedean assumption. Okay, so now I said we want to do this explicitly. We want to write this down as a semi-definite program. This is the matrix that's giving the constraint for the moment represent moment relaxation. We can write this matrix by the moments and with some coefficient matrices A alpha. This is a symmetric matrix and there's this nice box structure. And we can define two operators which are adjoint to each other. The one direction is you take the functional and map it to this matrix right here. And the opposite direction is you take symmetric matrix and map it to this functional, which takes the basis element, the alpha, to the trace of the matrix with this coefficient matrix. Okay. And then you do this, you write it down as a semi-definite program. So left-hand side is still a the moment relaxation over the cone of the functionals on the space of which degree at most 2D. Dual cone of this is 0. The dual formulation is over the cone of symmetric semi-definite matrices, which is self-loop. And then it's a technicality to show that the optimal value of this one right here with the sum of squares relaxation, and that duality gap is given by the trace of the optimal matrices for the primal and dual formulation. So is it good to do this? Do we gain something? Do we lose something? That's the big question. We already showed convergence, so it works out in theory. Okay. So let's say we fix some relaxation order, and we denote by m and n the number of matrices of this semi-definite program and how large these matrices are. So I'm not taking into account here that this matrix has block structure. It's something that you can maybe exploit in the SDP solver, but for simplicity, let's not do this here. This table shows how large these matrices are. And let's just look at two entries, which are very interesting, I think. These two right here. They are obviously different from each other. But the interesting thing is, these groups, B4 and C4, I'm not telling you what they are, but they are isomorphic. So what we are doing here is essentially optimizing the same trigonometric polynomial. We rewrite it in the generalized Chebyshev polynomials. But then, because the root systems associated with these groups are different, you obtain a different notion of weighted degree. And these notions lead to much smaller matrices and much finer hierarchy, essentially. So as you can see, we can define these hierarchies for the same values from 4 onwards, all the way to, I think you can go on further like that. But you can see that matrices needed in the B4 case are almost 3 times smaller than the matrices needed in the C4 case. And their size is also almost 3 times smaller here. Yes. We checked that, and interestingly, so we did not do any in-depth analysis with flat extension to see that this is actually optimal, but they are very close to each other, and it's very strange. I mean, the reason why this is happening is related to the root system, and this is easily explainable. But you need much smaller matrices to obtain the same result. And I will give an example on a later slide.
So do you have to go that far in the hierarchy to get
No.
flat extension?
Oh, so as I said, flat extension is something that we did not investigate because I think this weighted degree gives a problem. You know, when you measure on D+1, but now +1 is not enough. You need to go higher to catch this weighted degree. And I think it's easy to, it's maybe possible to adapt the proof of for the flat extension, maybe with the border basis. But let's see, it's future work.
But the optimum you obtain, is it changing a lot? Yeah. With a D?
So I did a lot of numerical experiments for each of these cases. And I think what you see is that it's suboptimal in the beginning, and then when you go in the order high enough, say 6 or 7, stabilizes. But you really have to look at the how these values behave for the specific examples.
And what is the value of n here? Small n.
L?
No, small n, the number of initial variables. Maybe.
It's the index. Yeah. Yeah, sorry, I could have said that. So those are polynomials in 2 variables, 3 variables, 4 variables.
And what happens if now you don't exploit symmetries at all, and you just compute the?
It's the C4 case. In the C4 case, the weighted degree is the classical degree.
Okay. But I mean, without using this PMI relaxation,
Oh.
I mean, directly tackling the initial trigonometric polynomial optimization, what's happening here?
I guess you won't be able to see this value here because
This will be
when you So, okay, sorry. What I mean is, if you take the matrix that defines the orbit space, and you write it down with the minors.
No, I mean, even without exploiting any symmetry, without using this process Schwarz, without just optimizing the initial trigonometric polynomial.
I guess you would have to multiply everything with order of the groups. How many additional coefficients there are? We did not try to optimize the trigonometric polynomials themselves. We wanted to optimize with techniques from polynomial optimization. Okay, so as I said, the number of the decrease in the matrix size is very significant. So standard laptop, I was not able to solve here for the C4 case at already 10, but I was very well able to solve this problem right here. But the problem is to get these matrices that define the semi-definite program, because you need to calculate with orbit calculations the entries.
Maybe you will explain it, the P of Z matrix for all these groups is something very easy to compute.
The P matrix is very easy to compute. We have a very explicit formula for that. That just involves elementary calculations, like adding,
And the
multiplying.
size of it relates to what?
It's N. It's 2 by 2, 3 by 3, 4 by 4.
Okay.
Okay. What you can do when you have this semi-definite program that we mentioned before with the primal dual formulation is you can handle maximum problems. Say, for example, you want to find this value right here. You infimize the polynomial, but now you also optimize on the coefficients. And the coefficients are allowed to be in some finite set S. Then you can use a result in the book of Lasserre from 2009, which tells you how to do that. Essentially, what you need to do to the semi-definite program, you need to add the linear constraints that you have on the coefficients here. And it only works with linear coefficients. With linear constraints on this outer problem right here. Otherwise, this optimization problem is not semi-definite. And okay, I just wanted to say this quickly and maybe come to the final application that I was mentioning, maybe a problem in algebraic combinatorics, where you want to find the chromatic number of graphs. So the chromatic number of a graph is just the question, how many colors do you need, so that when you assign colors to the vertices of the graph, two vertices of the same color are not connected by an edge. You can generalize this notion to infinite graphs, or even graphs like Rn that are not countable. And here the graph to consider is like a set of vertices in Rn. And for a given norm on Rn, we say that two vertices are connected by an edge, if and only if the distance is 1. And in this case, you can speak of something like the chromatic number of this graph. To be precise, you need to speak of the measurable chromatic number, which means that the color classes need to be, the set of all points which are connected in this graph, these sets need to be measurable. And this problem was considered quite a long time ago by Hartiger and Nelson, who asked essentially this problem for the two-dimensional space with the Euclidean norm. And the funny thing is that this problem is not solved yet. It's not. So the chromatic number for this graph is known to be somewhere between 5 and 7, but this is all. And so this tells us that this problem is very difficult, and you can yet still find lower bounds for this chromatic number. And this was realized by Bashok, Ricord, Inria, and Valentin in 2014. gave a so-called spectral bound, which is a lower bound for the chromatic number. And a few years later came a result that tells us that this chromatic number is at most 2 to the n for Rn. If this polytope norm, if this norm that you have here is coming from a polytope, such as the hexagon we saw before, that is tidying the space. So what does it mean? Let's look at our previous example here, the hexagon. As I said, we want to optimize this polynomial right here. And now what we can do, because we have this max-min approach, we can do bilateral optimization if the constraints on the coefficients are linear. Then we can apply this in the spectral bound. What does the spectral bound say? It tells you if the norm is coming from a polytope, and you choose points on the boundary of this polytope, and you essentially index your trigonometric polynomial by these points, then you obtain a function that if you minimize it, it appears in the spectral bound. So background for this is you take a measure on the boundary and you take the Fourier transformation. This would be a trigonometric polynomial and appears in the spectral bound as follows. Lower bound is given by 1 minus 1 over the maximum over the coefficients and the minimum of this polynomial right here. Assuming that the sum of the coefficients is always 1. In general, this is the sum of the coefficients. And one thing that you can show quite easily is the chromatic number of this graph. So RQ with the norm given by the hexagon has chromatic number exactly 4. This is what you see on the right hand side. Those are the minimum and maximum colors that you need. Now the question is, how good is the spectral bound actually? And when you make this choice right here, you choose these points on the boundary, you can show that the optimal value of this polynomial right here, so we optimize on coefficients and on the z, is this value, which is unsatisfying because it's not 4, it's not the chromatic number. So maybe we can make a different choice for these points on the boundary. Maybe we can make them more dense to see what happens. And this is a table here, which is involving also a list of these moment relaxations. Give me 1 more minute.
Yeah.
So, what's going on here? This polytope has 2 symmetry groups. It is on one hand the symmetric group, where you, just clearly, if you draw a vertical line, for example, you can flip it and read vertex. But also the dihedral group, the 6 points, which is this P2 right here. So you have 2 groups at your disposal. And you can see that although the Chebyshev polynomials are a bit different, you are still optimizing the same trigonometric polynomial, and this is mirrored in the table right here. So if you take as supporting points for the chromatic number, these 2 right here, you obtain 3. If you take what we had before, these points on the boundary, you obtain this 3.57. And if you go higher, nothing changes. So this is what I was saying before, that increasing the order doesn't really do anything. In here, we increase the order along the rows, but the value does not improve. Okay. So let me make a conclusion here. Talk about how to optimize trigonometric polynomials by rewriting them as Chebyshev polynomials. We adapted the notion of the weight degree to essentially reduce the matrix size in the semi-definite program. And we exploited that the set on which we optimize is given by a matrix. And in the future, what I would like to do is maybe look into verifying the set extension to verify that we have finite convergence. And maybe one think about if it's possible to extract minimizers using the Chebyshev polynomials. And maybe quantify this gap that we saw between the chromatic number and the spectral bound that we computed actually. So Thank you for sticking with me.